All right, hello everyone, and welcome to the AI Research Roundup. I'm your host, Alex, and today we're looking at some really interesting AI research. We'll be discussing a paper titled Embodied-R, Collaborative Framework for Activating Embodied Spatial Reasoning in Foundation Models via Reinforcement Learning, which was published April 17, 2025. So, this paper tackles how AI models can learn to perceive and reason about space, spatial relationships, from visual sequences like videos. Think about how humans understand their surroundings from their own viewpoint. The researchers propose a framework called Embodied-R that cleverly combines large vision language models for perception with smaller language models for reasoning, using reinforcement learning to achieve a kind of slow thinking process. And speaking of how they did this, the researchers have actually made their code public. What we're looking at here is a screenshot of their GitHub repository for the Embodied-R project. So it's all there. The setup instructions, how to prepare the data, and the actual code for running the VLM perception part, the LM reasoning part, and that reinforcement learning training we mentioned. It's great to see this open sourced, allowing others to reproduce their work and, build on it. Okay, so to give you a better picture of what kind of problems Embodied-R is designed to solve, take a look at this figure. On the left side, it shows different types of embodied spatial reasoning tasks, like understanding your position, predicting outcomes, or planning routes, using visual data from both indoor and outdoor scenes. And then, on the right, it illustrates the difference between, fast thinking, which is like a quick jump to an answer that might be wrong, and the slow thinking process that Embodied-R encourages, where the model actually reasons step by step, analyzing the video sequence in relation to the question before arriving at a hopefully more accurate answer. Okay, so building on that idea of slow thinking, this figure really lays out the Embodied-R framework in more detail. You see the video input on the left, along with the spatial reasoning question. Well, instead of processing every single frame, they use a keyframe extractor first, which is pretty smart for efficiency. Then, those keyframes go into the large vision language model, the perception part, which pulls out semantic information frame by frame. This understanding then feeds into the smaller language model, the reasoning part, which is trained using reinforcement learning to generate that structured think, then answer response. And importantly, look at the top. The reward system for that training includes not just accuracy, but also checks for the right format, and introduces this logical consistency reward to ensure the reasoning itself is sound. Okay, and speaking of that collaborative framework, how much does that collaboration actually help? Well, this table here, Table 3, really digs into that. It's showing an ablation study, basically comparing the performance with the full collaborative setup, that's the W row, versus without it, the W/O row, likely just using the large vision model alone. And, look at the average accuracy across all tasks, the AVG column. It jumps from about 34.8% without collaboration, up to 51.1% with it. That's a pretty significant boost, over 16 points, showing this collaborative approach really works. Okay, and remember earlier we mentioned that keyframe extractor component? The part that selects important frames instead of processing the whole video? Well, Table 2 here gives us a closer look at its impact. It compares performance with the extractor, that's the W row, versus without it, the W/O row. You can see using the extractor drastically cuts down the average number of frames from 32 to about 21, saves significant time on training and especially inference. Look at that. Inference time drops by about a third, while only causing a very small drop in accuracy, just 1.6%. So, it's a really effective way to make the whole process more efficient. So, we've seen how the collaboration and the frame extraction help. But how does Embodied-R actually perform against other existing models? Well, Table 1 here shows exactly that. It compares Embodied-R down at the bottom against a bunch of others, like proprietary models, state-of-the-art reasoning models, and open-source ones across various spatial reasoning tasks. And, the key takeaway is the average accuracy. Embodied-R hits 51.1%, which is substantially higher than even models like Gemini 2.5 Pro at 40.8% or GPT-4o at 35.7%. It really demonstrates the effectiveness of this framework. Okay, so that table gave us the overall average scores, but this radar chart here gives a nice visual breakdown of how Embodied-R, that solid yellow line and shaded area, stacks up against the others on the specific spatial reasoning tasks mentioned earlier, like route planning, appearance order, relative distance, and so on. You can really see how Embodied-R tends to cover a larger area overall, especially excelling in tasks like appearance order and landmark position compared to the dashed lines representing the other models. It visually reinforces that strong performance we saw in the average scores. Alright, so those charts showed us the numbers, but this figure here, figure 3, gives us a couple of specific examples, actual case studies, that really illustrate how Embodied-R's slow thinking works compared to others. We see two tasks, landmark position on the left and relative distance on the right, along with the video snippets, and, well, look at the outputs. Embodied-R clearly shows its step-by-step reasoning inside those think tags, analyzing the scene and options before giving the correct answer. The other models, like Qwen or Gemini here, they seem to get confused or jump to the wrong conclusion, missing key details from the frames. It really highlights how that structured, slow reasoning process helps achieve better accuracy and logical consistency. Okay, so those examples really show the difference that structured reasoning makes. Ultimately, Embodied-R demonstrates how combining collaboration, frame extraction, and reinforcement learning can significantly enhance the spatial awareness of foundation models. It's a really promising direction for creating AI that can navigate and understand our physical world more effectively. That's all for this segment. Thanks for joining me on the AI Research Roundup. I'm your host, Alex.